Standard Deviants present The Deep Fried World of Organic Chemistry Part 2. Starring Galila Azrez, Herschel Bliefeld, Beth Kirkpatrick, Jeremy Clavens, Tessa Monroe, Sean Powell, Gabrielle Smith, Shannon Ward, Chaz Maston, Ashley Fleming, Billy Portman, Rob Cohen, Kerry Washington, and Brad Aldis.
Hi, I'm Sean Powell. Welcome to the Deep Fried World of Organic Chemistry Part 2. Get ready to shake and bake with all the organic chemistry concepts you need to know. For the next 2 hours, we're going to be talking about crazy things like electrophiles, nucleophiles, reaction energy diagrams, alkenes, electrophilic addition reactions, carbocations, Markovnikov's rule, and Hammond's postulate, just to name a few.
And now it's that moment we've all been waiting for. Disclaimer time. In order to fully grasp the intricacies of organic chemistry, you have to go to class, read your book, and listen to your professors. So do all that. Don't make us look bad.
Remember that we're on videotape. You can fast forward the tape through sections you already know, pause the tape if you need to take notes, and rewind the tape if you need to see something again. And if you never want to see us again, well, a deep fryer works really well.
Remember, this is the Deep Fried World of Organic Chemistry Part 2. So in this video, we're going to assume you know everything we covered in the Deep Fried World of Organic Chemistry Part 1, like the basic concepts of general chemistry and the fundamentals of organic chemistry, including the hybridization states of carbon, naming hydrocarbons, and the conformations of alkanes and cycloalkanes.
Enough already, let's get on with it. I got a life here.
Part 1. Introduction to Organic Reactions.
In video 1, we introduced you to a basic group of organic molecules, the alkanes. In this video, we'll go over another group of organic molecules, the alkenes. We'll also take a look at how alkenes behave in reactions. Before we can get into a big discussion on the different types of organic reactions, though, we need to talk about functional groups.
Section A, Functional Groups.
Functional groups are fun little additions to organic molecules which give them their individual flavors, sort of like cumin.
So here's the beef on functional groups. 1. A functional group is always the same atom or group of atoms. 2. A functional group behaves the same way in a reaction. 3. Reactions take place at functional groups. So, if you know where the functional group is, you know where the reaction is going to take place. And finally, 4. We put all of this together. If you know where the functional group is and how the functional group behaves in a reaction, then you know where the reaction will occur and you know what kind of reaction is going to take place. This will all make sense in a moment once we do some splaining, Juicy.
Okay, wait. Before we really get into the different functional groups, we need to say something. You see, we're eventually going to see how all of these different organic molecules and their functional groups are formed in this tape and in tape 3. We'll also learn about the different reactions that these groups participate in. But for right now, we're just going to give you a really cursory glance at the different kinds of organic molecules and their functional groups.
Don't worry about how you make these molecules. We'll get to all of that. Just keep your pants on.
Whoops.
In the first tape, we spent a lot of time on alkanes, which only contain carbon, hydrogen, and single bonds. Alkanes are sort of like ground zero for organic molecules. They have no functional groups and so aren't really reactive.
Because alkanes only have single bonds, and because they don't have any functional groups, and because they aren't reactive, alkanes are often called paraffins. The word paraffin literally means too little affinity. That just reinforces the idea that alkanes, or paraffins, have little or no affinity for reactions.
And here's yet another way to think about alkanes. There's a hydrogen every place that there can possibly be one. Alkanes are saturated with hydrogens.
Now we need to look at four different functional groups, which will come up again and again in this tape and in tape 3.
Functional group number 1 is the double bond in an alkene. Again, don't worry about what an alkene is or how you make one. For right now, all you need to know is that the functional group of an alkene is a double bond between two adjacent carbons, and that the double bond in an alkene will always behave the exact same way in a reaction. When an alkene participates in a reaction, the reaction takes place at the double bond.
By the way, like we said, alkanes are relatively unreactive because they're completely saturated with hydrogens. Alkenes, on the other hand, don't have a hydrogen every place there possibly can be one. 2 are missing, and that's why there's a double bond. So alkenes are said to be unsaturated.
Functional group number 2 is a triple bond in an alkyne. The functional group of an alkyne is a triple bond between two adjacent carbons. Anytime an alkyne participates in a reaction, the reaction will take place at the triple bond. Alkynes are also unsaturated.
Functional group number 3 is a halide. Let's say we have a regular old alkane. If we remove one of the hydrogens on the alkane and replace it with a halogen, we get a molecule called a haloalkane. The halogens are found in column 7A of the periodic table, and they include fluorine, chlorine, bromine, and iodine. If one of these suckers is stuck on a carbon somewhere, you've got yourself an alkane with a halide functional group. If a haloalkane participates in a reaction, the reaction will take place at the halogen.
Just one more functional group to go. If you remove a hydrogen from an alkane and replace it with a hydroxyl group, OH, you get an alcohol. So, anytime you see a hydroxyl group, OH, attached to a carbon of an alkane, you've got an alcohol.
Those are the only functional groups we're going to look at right now. But there are about 10 more that we usually discuss in organic chemistry. Instead of introducing them all right now, we'll wait until they come up. What you need to get out of this whole discussion is learn your functional groups and know how to identify them.
By the way, want to know some pretty neat everyday applications of organic chemistry? Check this out. This is olive oil. Olive oil, besides being a goofball character from Popeye, is an unsaturated fat. That means there are double bonds in it. Double bonds make chains of carbons all kinky. Because of all these kinks, olive oil molecules can't fit together really tightly. That's why olive oil and other unsaturated fats like corn and vegetable oil, are liquid at room temperature. Animal fats, on the other hand, are saturated. That means they primarily contain single bonds. Because there aren't many kinks in saturated fats, they can hang together really tightly. That's why saturated fats like lard and butter are solid at room temperatures. Okay then, so what's margarine? Margarine is a combination of butter and vegetable oils. But why is margarine solid? Why isn't it a liquidy oil floating around on solid animal fat? Well, margarine contains partially hydrogenated vegetable oil.
In the deep-fried world of organic chemistry, Part 3, we'll be looking at a hydrogenation reaction. In that reaction, you take a double bond, just like you find in vegetable oil, and you add hydrogen to it. That breaks up some of the double bonds in the vegetable oil and makes them single bonds. If you break up enough of these double bonds, you'll make enough single bonds that the vegetable oil will stick together at room temperature. The vegetable oil has been partially hydrogenated, making it a more saturated fat, making it semi-solid and spreadable at room temperature, and making it oh so bad for you.
Now that we know about functional groups, we need to learn about the different types of organic reactions.
Section B, organic reactions.
Organic compounds undergo changes that fall into 4 general types of reactions: addition, elimination, substitution, and rearrangement reactions.
If we can predict how an organic molecule will behave, we can predict which one of these 4 reactions will occur, and we'll also be able to predict what the product of the reaction will be.
I wonder what the reaction will be.
Organic chemists do this all day, synthesizing new and exciting organic compounds, like aspirin. They do this by modifying molecules and combining them with other molecules in very specific ways.
Let's look at 4 different kinds of organic chemical reactions. Okay, guys?
And away we go.
The first type of organic reaction is an addition reaction. In an addition reaction, 2 molecules come together to form one larger, more complex molecule. The overall formula for an addition reaction is 2 different molecules, A and B, react to form one single molecule, C. Kind of like when you combine an elephant and a giraffe and you get an eliraph. See, A and B react to form product C.
Jerfant, eliraph. Jerfant, eliraph.
The second type of organic reaction is
An elimination reaction.
elimination reactions are basically the opposite of addition reactions. A single molecule splits to form 2 smaller molecules.
The overall formula for an elimination reaction is a single molecule, A, splits to form 2 new molecules, B and C. So here, the eliraph
Jerfant.
splits back into an elephant and a giraffe.
Organic reaction numero 3.
Substitution!
In a substitution reaction, 2 molecules come together and switch parts, forming 2 new molecules. The formula looks like this.
The reactants A, B, and CD switch component parts to form 2 new products, AC and BD.
Now swing your partner, do-si-do. Don't step on your partner's toe. Woo!
And finally, in the fourth type of organic chemical reaction, a rearrangement reaction, a molecule rearranges itself to form a new compound. Because the new product is simply a rearranged version of the original reactant, the reactant and product are isomers of one another.
Isomers are compounds that have the same molecular formula, but which have different structures. Makes sense, right? Because you can't get more out of a reaction than you put into it. In a rearrangement reaction, the product is just a rearranged version of the original reactant molecule. The formula for a rearrangement reaction looks like this. The reactant A rearranges itself to yield a new product, B. A and B are isomers.
By the way, for the rest of this tape and tape 3, we're only going to be looking at addition reactions, in which A and B come together to form a larger product, C. We need to take a long, involved, in-depth look at addition reactions. So, buckle your seat belts. It's going to be a wild ride.
We know the overall view of what kinds of organic reactions take place. What we don't really know is what all the different types of organic compounds are yet. But that's okay. We're going to get to that in a second. First, what we have to... Excuse me. First, we need to take a more in-depth look at all the different things which are going on when these reactions take place. There are many factors at work in an organic reaction, each of which contributes to the overall reaction process.
These different steps, added up, make up the reaction mechanism, which is a detailed description of all the bond making and bond breaking that's going on as the reaction tries to make it from reactants to products.
In the first video, we learned all about covalent bonds, in which electrons are shared between atoms. We also learned that most organic molecules are held together with covalent bonds.
When we consider an organic chemical reaction, we're really only talking about either breaking or creating covalent bonds between atoms in organic molecules.
Covalent bonds can be broken in two ways, heterolytically or homolytically. Let's take a look at a basic reaction in which AB splits to form two new products, A and B.
AB on the left side of the arrow is the reactant, and A and B on the right side of the arrow are the products. Notice that the two components of the reactant AB are joined in a covalent bond. The two dots between them symbolize that A and B each share the two electrons in the covalent bond.
When the reactant AB splits up, the two electrons can break up so that one goes with one product and the other electron goes with the other product. If the two electrons in the covalent bond between A and B split up so that one electron goes with A and the other goes with B, the bond between A and B has broken homolytically. This is an example of homolytic cleavage. The word cleavage just means that a bond has broken.
Homo means same, and indicates that the two products of the cleavage reaction both have taken the same number of electrons from the broken bond, which, in this case, is 1.
On the other hand, when AB splits up, the two electrons that were in the covalent bond between A and B can go to one of the two products. In this case, the two electrons in the bond between the reactant AB will both go to product B and none to product A. If the two electrons both go to the same component, we say that the covalent bond between AB has cleaved heterolytically. This is an example of heterolytic cleavage.
Hello and welcome. Here we are on the waterfront. I'm here with Nigel, who's going to answer some questions from me. All right, see if we can get to the bottom of some of these questions. All right, Nigel, tell me about your first experience with heterolytic cleavage.
Well, that's rather personal. I'd rather not answer that. Perhaps we could move on to the next question.
Oh, that's no problem. I understand. These things can be a bit touchy.
The prefix hetero means different and indicates that the two products have different numbers of electrons from the broken bond. In this case, A has 0 electrons and B has 2. Another thing to notice about the reaction we just showed you is the use of arrows to indicate where the electrons go.
In the example of homolytic cleavage, we used half arrows to show that one of the two electrons from the covalent bond went to one product, and the second of the two electrons went to the other product. These half arrows look like fishhooks. In the example of heterolytic cleavage, we used a full arrow to indicate the movement of two electrons to one of the products. Get used to seeing these arrows, because they're going to be all over the place soon.
Okay, so now we have these new products which have formed as a result of an elimination reaction. And the number of electrons each of the products has is dependent on whether the reactant of the reaction cleaved homo or heterolytically.
The products of homolytic cleavage both have one electron, and we call them radicals. A radical has an odd number of electrons in its outer valence shell, and therefore has an unshared electron. Because of this unshared electron, a radical is on the lookout for another radical to form a bond with.
But radicals aren't picky. A radical will also hook up with some other source of electron density in order to refill its valence shell.
Reactions which cleave homolytically produce two radicals, and therefore are called radical reactions.
On the other hand, reactions which cleave heterolytically produce one component with no electrons and one component with 2 electrons. Think about it. These 2 electrons were shared in a covalent bond, which means that each component of the reactant gave 1 electron that it already had to the covalent bond. When the bond split heterolytically, one of the component parts came away with 2 electrons, while the other got gypped and came away with 0 electrons.
Hey, what's up with that, man?
Oftentimes, the new product with 2 electrons has an overall negative charge because it comes away with 1 more electron than it was initially contributing to the covalent bond. There's a name for this type of species, an anion. The product with 0 electrons will have a net positive charge because it's missing the electron it was initially contributing to the covalent bond. We call this species a cation.
Think anion, onion, negative. Cation, cat, positive.
We here at the Onions Are for Lovers Committee, hello little friend, resent the implication that onions are in any way negative, like an anion.
The 2 products of a heterolytically cleaved neutral reactant are ions. They carry charges and are therefore polar. They're an anion and a cation. Most of the reactions in organic chemistry are polar reactions, by the way. They involve anions and cations along the reaction pathway.
Polar reactions are all about the attraction between groups with electron deficiency and therefore a positive charge and groups with electron density and therefore a negative charge. Opposites attract, so 2 species with opposite charges attract each other, and the reaction which ensues is called a polar reaction.
Okay, we're going to digress here for just a second. Would you get a job, you freak? Look, electron density is a pretty awkward term, but you're going to be hearing it a lot throughout the rest of this tape and the tapes to follow. See, except for rearrangement reactions, organic reactions basically come down to which species has a lot of electrons and therefore is electron rich, and which species doesn't have a lot of electrons and therefore is electron deficient. A species which is more electron rich is looking to share some of its electrons, and a species which is electron deficient is looking to pick up a few electrons.
Oh, hello, electrons. Hey, what say we bond, huh? Me, you 2 guys, huh?
And that's the basis for organic reactions. Who's got what and who wants what? The point we're trying to hit home is that the source of electron richness will be looking for the source of electron deficiency, and vice versa.
It's time to introduce 2 really important terms, which we'll hear again and again: nucleophile and electrophile. The word nucleophile literally means nucleus lover. You see, a nucleophile is a species with an electron-rich atom. It has extra electrons, which it can donate to an electron-poor atom. Because a nucleophile is electron-rich, it's attracted to nuclei, which are electron-poor. That's why it's called a nucleophile. It loves them nuclei, just like a bibliophile loves them books, and a thickophile loves Alan Thick.
An electrophile is an electron lover. An electrophilic species is the opposite of a nucleophile. It's electron poor and can accept electrons from a species that's got electrons to share. It loves electrons, just like a francophile loves La Belle France.
Actually, while we're at it, we're going to introduce a 3rd term, attack, a verb which literally means to set upon forcefully, to threaten with immediate capture, to assail with unfriendly or bitter words. When we speak of electrophiles and nucleophiles, we'll often refer to them as attacking electrophiles or attacking nucleophiles. However, our electrophiles and nucleophiles aren't throwing insults at carbon. When we say that X attacks Y, we really mean that our electron-rich nucleophile is donating some of its electrons to our electron-deficient electrophile. It describes the attraction between electrophiles and nucleophiles as bonds form.
Hey, does any of this talk of electrophiles and nucleophiles sound familiar? Well, it really should. Remember from the first video that a Lewis acid can accept a pair of electrons from an electron donor. Lewis acids are electrophiles when they're on the attack. A Lewis base, though, can donate a pair of electrons. Lewis bases are nucleophiles when they attack electron-poor nuclei.
Did you hear that? It's gonna come back again and again. When a Lewis acid is on the attack, it's an electrophile.
When a Lewis base is on the attack, it's a nucleophile.
So, the 4 types of organic chemical reactions are addition, elimination, substitution, and rearrangement. If a reactant AB cleaves homolytically, then product A comes away with 1 electron from the covalent bond, and product B also comes away with 1 electron from the covalent bond. Both products, A and B, are called radicals. If reactant AB cleaves heterolytically, one of the products comes away with both of the electrons from the covalent bond, and we say it is an anion. The other product of the heterolytic cleavage comes away with none of the electrons from the covalent bond, and we say it is a cation. An electrophile is an electron-poor species which loves electrons. A nucleophile is an electron-rich species which loves electron-poor species.
Section C, reaction energy diagrams.
So we know that there are these 4 general types of reactions that take place. But what drives them? Do they just occur spontaneously? What makes bonds break and reform? Energy, my friends, energy! Energy is released when bonds are formed and absorbed when bonds are broken.
Some organic reactions, like burning wood, produce enough energy to heat our homes. Fire is a quick, violent reaction which produces lots of energy, enough to burn down a portion of Chicago, keep our homes toasty all winter, or roast an entire pig.
Of course, not all reactions are as quick or as violent as fire, but every reaction either absorbs or releases energy. We can represent the energy changes which occur during the course of a reaction using a reaction energy diagram.
A reaction energy diagram relates the changes in potential energy in a system as a chemical reaction occurs. Potential energy is the amount of energy that's stored in a system. You get potential energy when there are attractive or repellent forces between objects. Don't worry, this is all going to make sense in a minute.
In a reaction energy diagram, the reaction usually proceeds from left to right along the horizontal axis. On the vertical axis, we relate the relative change in potential energy in the system at that particular stage of the reaction.
The curved line which represents the changes in energy looks like a hill. The reactants in a reaction are on the left side of the hill, and the products are on the right side of the hill. Remember, reactants are what go into a reaction, and products are what you get.
So, as we said, the reaction proceeds from left to right along the horizontal axis of the energy diagram. The relative change in energy in the system is indicated along the vertical axis of the diagram. So, in this reaction, the reactants are at a lower energy level than the products. The reactants start out with less potential energy than the products end up with.
In other words, somehow the products come away from the reaction with more energy than we put into it. Do you see that here? The products on the right side of the hill are at a higher energy content than the reactants. Somehow, energy must have been added to the system. This tells us that the reactants had to absorb energy to form the products of the reaction.
We say that this reaction is endothermic. That's a pretty easy term to remember, since endo sort of sounds like into, and that tells us that energy is taken into the reaction.
Endothermic, into. Endothermic, into.
On the other hand, on this energy diagram, the reactants contain relatively more energy than the products. This means that the reactants had more energy between them than necessary to form the products of the reaction. Energy is therefore released in this reaction, and we say that the reaction is exothermic.
That's also a pretty easy term to remember, since exothermic sort of sounds like exit, and that tells us that energy exits the system.
Exothermic, exit. Exothermic, exit.
We've already mentioned that the curved line of an energy diagram looks like a hill, with the reactants on the left side of the hill and the products on the right. Now, looking at this hill, what it's telling us is that the potential energy level of the system starts out low, and then, as the reaction proceeds, the potential energy of the system increases. It maxes out at the top of the hill, and then the potential energy of the system decreases.
Okay, so why is this thing a hill and not simply an inclined plane going up or down? Well, think about it this way. The first thing that happens in most chemical reactions is that bonds are at least partially broken down, and at the same time, atoms which were once comfy where they were get all moved around.
It takes energy to break bonds and move atoms, so energy has to be put into the system. That's why the first part of the reaction goes uphill. But as the reaction keeps going, bonds are frequently made. Energy is released when bonds are made, and this has to be depicted in the diagram, so the hill has to go back
down.
If the energy reaction diagram only went uphill and never came back down, then we just keep putting energy into the reaction without ever getting a return on our investment, so to speak. By the same token, if the hill just kept going straight down, as though energy were constantly being released, then that would seem to imply that no work has to be done to earn some sort of reward. And we all know that there's no such thing as a free breakfast.
You see, this is true whether the reaction is endothermic or exothermic. Even if energy is released in a reaction, the reaction still has to work its way up to the top of the hill. I gotta start working out.
The crest of the hill represents the highest energy point along the reaction pathway, and it's called the transition state of the reaction. Transition being the key word here, as this point on the energy diagram signifies the transition from reactants to products.
One more point about energy diagrams and we're finished.
We can literally think about energy diagrams as hills. Imagine you're on a bike trying to ride up a grueling climb. If the climb is really steep, you'll use up a lot of energy, and it'll take you a much longer time to get over this steep hill than a shallower one. If an energy diagram has really steep, long hill, just like you on your bike, we know that the reaction will take a long time and use a lot of additional energy.
On the other hand, if you're riding over a small, relatively shallow hill, you'll have no problem getting over it on your bike. Same thing with reactions. The full course of the reaction will take place very quickly and won't use up a lot of energy.
Notice that we're talking about how much time it'll take a reaction to occur. We're not saying anything about whether the reaction is endo or exothermic. We can only determine that depending on where the energy levels of the reactants and the products are in relation to each other on our energy diagram. But just by looking at the height of the hill on the diagram, we can say whether the reaction is fast or slow.
When we get more into the different types of organic chemical reactions, we'll use these energy diagrams even more, particularly when we discuss choices or competition between two possible reactions.
And what does that mean? Well, as you'll soon see, everything in organic chemistry comes back to energy. Reactions wimp out and try to take the path of least resistance, the path which keeps the transition state of the reaction as low as possible.
It's tempting to call these reactions lazy, good-for-nothing reactions. But out of politeness, we say that these kinds of reactions are kinetically controlled because they're trying to make it through the reaction without expending a drop more energy than they have to.
On the other hand, other types of reactions are willing, if they absolutely must, to spend more energy if it means that the product of the reaction is more stable. I guess it's a whole ends justify the means type of thing or something. These kinds of reactions are thermodynamically controlled.
We're not going to spend a lot of time on this now, but the point that we're trying to make is that some reactions are favored over other reactions, simply because kinetically controlled reactions are easier energy-wise. In some reactions, the kinetically favored and the thermodynamically favored reaction paths are the same.
A reaction energy diagram measures the relative amount of potential energy in a system. The reaction proceeds from left to right along the horizontal axis, and the change in potential energy in the system is measured along the vertical axis. The reactants are on the left side of the hill. The crest of the hill is a special place called the transition state, and the products are on the right side of the hill.
If the reactants are at a lower energy level than the products, then energy is absorbed for the reaction to take place. This type of reaction is endothermic. If the reactants are at a higher energy level than the products, then energy is released. This type of reaction is exothermic.
Before we can really discuss the different types of reactions, though, we have to understand a little more about the different types of organic molecules. There are way many more organic molecules than just the alkanes. Next, we're going to take an in-depth look at alkenes.
Part 2, the alkenes.
Section A, Introduction.
In the first video, we learned that alkanes are organic compounds which contain only hydrogen, carbon, and single bonds. Alkenes, on the other hand, are organic compounds which contain only hydrogen, carbon, single bonds, and at least one double bond. Double bonds form between sp2 hybridized carbons. We haven't really taken a good look at multiple bonds yet, but we'll get to that in a little while. First, let's learn about the basics of alkenes, like what they look like, how we name them, and how they spend their weekends.
Ethylene is a lovely little alkene, the simplest of all alkenes. But don't mistake that simplicity for naivete. Ethylene likes long walks on the beach, sunsets, and sharing single drinks with 2 straws. Ethylene is looking for a caring, compassionate electrophile who isn't afraid of commitment. If you think you are the electrophile ethylene wants to react with, call the Love Line at 1-800-238-9669.
As we saw in the Deep Fried World of Organic Chemistry Part 1, the general chemical formula for an alkane is CnH2n plus 2. On the other hand, the general chemical formula for an alkene with 1 double bond is CnH2n. N tells us how many carbons there are in our molecule.
We already know that a single covalent bond is made up of 2 electrons. Double bonds, however, are made up of 4 electrons, so the alkene has 2 extra electrons tied up in this double bond, and therefore 2 fewer electrons bonded to hydrogens or other substituents. Now, let's figure out how we name these babies.
Hi, I'm Chip Pausek. As co-president of Cerebellum Corporation, I'd like to say how pleased I am that the writer of this tape chose not to put in a silly pun about naming babies. Instead, she chose to have me stand here and tell you how proud I am that she didn't put in a silly pun about naming babies.
Section B, naming alkenes.
If you've mastered naming alkenes will be a breeze. If naming alkanes is still a little hazy, maybe you should check out the first video again. Or else get some new glasses.
Let's try to name this alkene. Step 1 of naming alkenes. Find the longest continuous chain of carbons which includes the double bond. The longest chain of continuous carbons in this molecule has 6 carbons, but it doesn't include the double bond. The longest continuous chain, which contains the double bond, has 5 carbons. Since this 5-carbon chain contains the double bond, it's the main chain of the hydrocarbon.
To name this main chain, we use the same prefixes we use when naming alkanes. The prefixes like eth, prop, bute, pent, and so on. This time, however, we'll use the suffix ene to denote that the main chain hydrocarbon is an alkene. This hydrocarbon, with 5 carbons and 1 double bond, is some sort of pentene.
Step 2. Number the carbons, starting at the end of the chain closer to the double bond. If there's more than 1 double bond and both are equidistant from the ends of the hydrocarbon, start at the end closer to the first branching point. Just make sure that the double bond has the lowest number possible. We'll number this pentene from right to left so that the double bond begins at carbon 1.
But we're not finished yet. We also have to indicate where in the pentene the double bond is located. In this case, the double bond is between the first and second carbons. To indicate this in the name, we say that the main chain of this molecule is 1-pentene. The 1 tells us that the double bond begins at the first carbon. The prefix pent tells us that there are 5 carbons in the main chain, and the suffix -ene tells us that the main chain has a double bond in it and is an alkene.
Okay, notice something for a second. Why didn't we call this molecule 1,2-pentene? Well, if the double bond begins at carbon 1, then it must end at carbon 2. Putting all that in the name would be just a statement of the obvious.
Now it's time for a statement of the obvious.
Tomorrow, there's a chance for weather.
Now that we've got the main chain of the molecule named, we have to move on to step 3. In step 3, we figure out where all of the substituents to the main chain are, and we name them.
There's only one substituent on the main chain. It's got 2 carbons, so it's an ethyl group. It's on the second carbon of the chain, so we'll call this substituent 2-ethyl. Put it all together, and the name of this molecule is 2-ethyl-1-pentene.
Okay, so the overall process for naming alkenes is, step 1, find the longest continuous chain of carbons that also contains the double bond. Step 2, number the carbons of the main chain so that the double bond has the lowest number. Step 3, name and number all of the substituents. Then you just put all the parts together, and you're an alkene naming fool!
Let's try this with another alkene. This is a cycloalkene. A cycloalkene, aside from being a fantastic name for a supervillain, is a cyclic hydrocarbon with double bonds. Step 1. The longest continuous chain of carbons that contains the double bonds is the 6-carbon ring. So this is our main hydrocarbon. We'll get to what you call this sucker in just a second.
This hydrocarbon ring has 2 double bonds, and we have to get that across in the name of the molecule. If there's more than 1 double bond in the molecule you're attempting to name, use the prefixes di, tri, etc. in the name of the main hydrocarbon. So let's name this thing.
It's got 6 carbons arranged in a ring, and the ring contains some double bonds. 6 carbons in a ring, double bonds. This thing is a cyclohexene. But wait, there are 2, count 'em, 2 double bonds in this hydrocarbon ring, and we have to use our prefixes to indicate this in the name of the molecule. There are 2 double bonds, so we'll use the prefix di, and the name becomes cyclohexadiene.
Notice that the prefix di is placed right in front of the suffix -ene. Well, di means 2, and -ene means double bond. So that sort of makes a lot of sense, doesn't it?
All right, we just figured out we're dealing with cyclohexadiene. Step 2 says that we have to number the carbons of this molecule. When numbering carbons of cycloalkenes, always start by numbering one of the carbons of the double bond so that the double bond is between 2 carbons with the lowest possible numbers. In other words, in a cycloalkene, carbon number 1 is automatically one of the carbons of the double bond. Check it out.
Here are 2 double bonds. In this molecule, one of our double bonds also has a substituent attached. It kind of gets first dibs, so we'll number this carbon, which is attached to both a double bond and a substituent, good old number 1. Once we do that, the double bonds in this cyclohexadiene are at the 1st and 4th carbons. We have to say where the double bonds are in the name of the molecule, so the name of the main chain of this hydrocarbon becomes 1,4-cyclohexadiene.
Step 3 says that we need to name everything and put it all together. We have a 1-carbon substituent, a methyl group, on the 1st carbon, and we write this as 1-methyl. Put it all together, and this molecule is 1-methyl-1,4-cyclohexadiene.
Organic chemistry is a really exact science, but even organic chemists bend the rules sometimes. Take a look at this molecule. There are a total of 2 carbons in 1 double bond. Using the rules we just learned, we would name this molecule ethene. But this molecule was around before all those naming rules were established, and the scientists back then named this molecule ethylene.
Some chemists, however, go too far in bending the rules.
I think I'll name the new molecule I just created Bob.
Okay, so we spent quite some time figuring out how to name alkenes, but we haven't really taken the time to figure out what they look like in space. So let's take a look at alkene structure.
Section C, alkene structure.
In the deep-fried world of organic chemistry, Part 1, we spent some time discussing the different spatial arrangements of alkanes because alkanes only have single bonds and because rotation is possible around these bonds. But rotation isn't possible around double bonds. Lucky for us, because this means there are only a couple of arrangements alkenes can assume. To explain why this is, we have to take a closer look at double bonds, and especially the pi bond component of the double bond. Don't flip out. We'll explain.
There are 2 main components of double bonds, sigma bonds and pi bonds. Sigma bonds are just single bonds. And hey, we're pros by now at single bonds. We saw them all the time when we looked at alkanes.
The sigma bonds of double bonds result from the overlap of 2 sp2 hybridized orbitals on adjacent carbons. Sigma bonds are formed from this head-on overlap of the 2 sp2 orbitals.
In the deep-fried world of organic chemistry part 1, we said that one of the remarkable things about carbon is its ability to form different hybridization states depending on its needs in a given structure.
An sp2 hybridized carbon has 3 sp2 orbitals formed from mixing 1 s and 2 p orbitals. It also has 1 remaining p orbital. So, we have these 3 sp2 orbitals lying in a single plane, all about 120 degrees apart. Carbon has 4 valence electrons, so there is 1 electron in each of the 3 sp2 hybrid orbitals. The remaining p orbital is running perpendicular to the sp2 orbitals, and it contains the 1 remaining electron.
When 2 sp2 hybridized carbons join together to form a double bond, 2 of the orbitals on each carbon overlap. One of the sp2 orbitals on carbon 1 will run into an sp2 orbital on the other carbon. The overlap of these orbitals forms the first of two types of bonds between the carbons. This bond is the sigma bond. It sort of forms head-on and has a lot of electron cloud overlap centered between the nuclei, so it's the stronger type of bond within the double bond. Each sp2 orbital contains one electron, so this sp2-sp2 bond will be made of 2 electrons.
But at the same time, both of the carbons have these p orbitals running perpendicular to the sp2 plane. The two neighboring p orbitals are close enough together to overlap and share electrons to form a second type bond between the two adjacent carbons. But this sort of bond is a little different from the head-on collision sigma bond we looked at a second ago. This type of bond is called a pi bond. The two electrons involved in these pi bonds are above and below the sp2 plane rather than directly between the two adjacent carbon atoms, making the electrons very accessible to an approaching reactant.
Since the electronic glue of this pi bond is not a head-on collision between the carbons like the sigma bond, the pi bond is weaker than a sigma bond and is more easily broken. It's sort of like a sideswipe. So now we see that the electrons in pi bonds are more accessible than the electrons in sigma bonds, and we also see that it's easier to break pi bonds than sigma bonds.
It's easier to pull two cars apart that were involved in a sideswipe than two cars that were in a head-on collision, right? That sort of makes a lot of sense. Alkanes only have sigma bonds. They don't have any pi bonds, but alkenes do have pi bonds. Pi bonds make alkenes much more reactive than alkanes.
Pi bonds make alkenes more delicious.
So the two overlapping sp2 orbitals and the overlapping p orbitals are all busy overlapping to form this giant double bond. This leaves 4 remaining sp2 orbitals on the two carbons, each holding 1 electron, ready and willing to bond to substituent groups.
So, as we were saying, although rotation about a single bond is possible for an alkane, it's not possible for alkenes. In order to twist around the two carbons joined by the double bond, the pi bond would have to break, and that's not possible outside a chemical reaction.
Take a look at this molecule. There's a double bond and a total of 4 carbons, so this molecule is some sort of butene. It's actually 2-butene, because the double bond is between the second and third carbons. Anyway, carbons 1 and 4 are bonded to the carbons of the double bond. They aren't substituents per se, because they're part of the main chain, but they are substituents to the double bond, and there are 2 of them. We say that the double bond is disubstituted.
The prefix di tells us that there are 2 substituents. In this case, when we speak of substituents on a double bond, we're talking about anything attached to the carbons of the double bond other than hydrogen. If there were 3 substituents on the double bond, we would say that the double bond is tri-substituted. We're actually going somewhere with this. Just hold on a sec. Let's go back to 2-butene.
The 2 substituents on the double bond, which in this case both happen to be methyl groups, are also on the same side of the double bond. But take a look at this other molecule. It has all the same components of the 2-butene we just looked at, and all of the components are in the exact same order, except that in this case, the 2 substituents on the double bond are on opposite sides of the double bond.
When both substituents of a disubstituted double bond are on the same side of the double bond, we are looking at the cis form of a molecule. Cis sort of sounds like same, so remember that a cis form of a molecule has both substituents on the same side of the double bond.
If, however, both substituents of the disubstituted double bond are on opposite sides of the double bond, we are looking at the trans form of the molecule.
Okay now, I don't know about you, but trans sort of reminds me of a cross. Kind of like transportation seems like I'm going across a state or something. I don't know, but maybe it'll help you out if you can remember that trans is kind of like a cross. So a trans molecule has 2 substituents across a double bond from one another.
The cis and trans forms of a molecule are almost exactly the same, except for the spatial orientation of their components.
There's a special name for these cis and trans forms of 2-butene. We call them stereoisomers. Stereoisomers are similar to isomers, but with unbelievable sound quality. Additionally, stereoisomers are a special type of isomer. Remember, isomers are different compounds that have the same molecular formula.
Two molecules which are stereoisomers of one another, then, have exactly the same atoms, and those atoms are arranged in exactly the same order. The only difference is the way their atoms are arranged in space.
Here are the cis and trans forms of 2-butene again. Both have exactly the same number of carbons and hydrogens. Those carbons and hydrogens and even the double bond are all in the exact same order. The only difference between the two is the way the atoms are arranged in space. One form of the molecule is the cis form, and the other form is the trans form.
Okay, quick side note here. If we take this methyl group on the end of the 2-butene molecule and stick it on what is now the middle carbon of a 3-member chain, we get 2-methylpropene. 2-methylpropene and 2-butene are isomers of each other. You see that? They both have the exact same number of carbons and hydrogens, and single and double bonds. But those atoms are not attached in the same order. 2-methylpropene and 2-butene are isomers, but they are not stereoisomers.
Look, we're not going to get into a lengthy discussion on stereoisomers right now. All right. For now, we need to get back to 2-butene.
2-butene is a rugged individualist who loves the outdoors. At one with nature, he enjoys fishing and camping, all the while treading lightly over Mother Earth. 2-butene is looking for a fun-loving electrophile who wants to react with his delicious pi bond. Interested? Call the Love Line at 1-800-238-9669.
The cis form of 2-butene is called cis-2-butene, and the trans form is called trans-2-butene.
Right. So this is all well and good if we're only talking about a double bond with one thing stuck on each of the carbons of the double bond. But what if our double bond has 3 or even 4 substituents? Well, in that case, we really can't call one group cis and the other trans because we wouldn't know which groups we were comparing. Instead, we use the EZ system of nomenclature. Take a look.
Where should I take it?
When naming tri or tetra substituted alkenes, which are alkenes with 3 and 4 substituents respectively, we have to use the EZ system of nomenclature. Basically, we're going to be comparing the substituents on one carbon of the carbon-carbon double bond to the substituents on the other carbon of the double bond. We'll start by drawing a line through the center of the double bond so that the 2 carbons and their substituents are separated from each other.
Here are 2 isomers of 2-chloro-2-butene. We'll start with the isomer on the left. By drawing a line down the center of the molecule through the double bond, we separate and are able to compare the substituents on carbon 3 with the substituents on carbon 2. Carbon 3 has 2 different substituents, hydrogen and methyl. We told you just a little while ago that hydrogen isn't considered a substituent. It isn't really, but we'll consider it one for the sake of comparison.
What we're going to do here is compare the 2 forms of 2-chloro-2-butene by looking at each of the atoms on either side of the double bond. And we're going to compare the atoms using their atomic numbers. This will all make sense when we do an example. Let's go back to that isomer of 2-chloro-2-butene that we were just looking at.
The first substituent on carbon 3, hydrogen, has the lowly atomic number of 1. The second substituent on carbon 3 is a methyl group, CH3. We're only comparing the first atom of each substituent. So for methyl, we'll consider the atomic number of carbon, which is 6.
Carbon has a greater atomic number, and we give it priority over hydrogen. Or we say that carbon has higher priority and hydrogen lower priority.
On behalf of the Fairness to Hydrogen Committee, we resent any implication that hydrogen has a low priority. We think hydrogen is pretty keen.
Now we move on to the substituents on carbon 2, which are chlorine and methyl. Chlorine has an atomic number of 17, and the carbon on the methyl group has an atomic number of 6. Therefore, the chlorine has higher priority and the carbon lower priority.
Now we determine whether this isomer has an E designation or a Z designation. E means that the high priority substituents are on opposite sides of the double bond, and it comes from the German word entgegen, which means opposite. Z means that the high priority substituents are on the same side of the double bond. Z comes from the German word zusammen, which means together. The high priority substituents on carbons 2 and 3 of our isomer are on opposite sides of the double bond. So we call this isomer E 2-chloro-2-butene.
Now we have to do the same thing with the other isomer. The two substituents on carbon 3 are hydrogen and methyl, and the carbon on methyl will have a higher priority than the hydrogen. On carbon 2, the two substituents are methyl and chlorine. Chlorine will be given top priority here. Now if we compare both sides of the double bond, we see that both higher priority substituents are on the same side of the double bond, so we give the isomer a Z designation and we name the isomer Z2-chloro-2-butene.
Okay, so let's say that you compare the first atoms of two substituents on the same carbon atom, and you can't determine priority. That could happen if the first atom is the same on each substituent. Maybe each are carbon atoms or something. No problem. Just move to the second or third atoms of the substituents until you are able to find a difference in atomic number.
And basically that's it. There were thousands of possible conformations for alkanes, but the double bond portion of alkenes is really limited. Alkenes can have cis or trans isomers, or E and Z isomers. That's easy, huh? One more quick point.
Let's say you get a molecule which has two of the same substituents on one carbon. That happens in the case of molecules like 2-methylpropene. There are two of the same substituents on one carbon, so that molecule won't have any stereoisomers, so it won't be cis or trans or E or Z. In other words, since both substituents are identical, they're interchangeable and there will be no possibility of stereoisomers. Trust us.
This is a good place to mention the term steric strain. We came across this in video 1 with alkanes, but we called it van der Waals repulsion. Steric strain occurs when two substituents get close to each other and get in one another's space.
Excuse me!
Steric strain occurs when two substituents end up really close to each other, like what happened in the cis isomer we just looked at. In our cis isomer, the two substituents are on the same side of the double bond.
Okay, they're closer together than they would be if they were arranged trans to each other, but the molecule can't do anything about it. Atoms can't rotate about double bonds. To rotate around a double bond, the pi bond would have to be broken open. The cis form of the molecule is stuck in this position with these two substituents which just can't get along.
Steric strain, therefore, makes most trans isomers energetically more favorable than cis isomers.
So wrapping all this up, a double bond is made up of one sigma bond and one pi bond. The electrons in the pi bond of a double bond are very accessible. Isomers are different compounds that have the same molecular formula. Stereoisomers have exactly the same number and order of atoms, but those atoms are arranged differently in space.
When two substituents on a double bond are on the same side of the double bond, those substituents are cis to each other. When two substituents on a double bond are on opposite sides of the double bond, those two substituents are trans to each other.
If there are more than two substituents on a double bond, use the EZ system. Prioritize the substituents on each carbon according to which substituent has the higher atomic number. If both high priority substituents are on the same side of the double bond, that's the Z form of the stereoisomer. If both high priority substituents are on opposite sides of the double bond, that's the E form of the stereoisomer. Steric strain occurs when two substituents get too close to each other.
All right, we're finished with our discussion of alkene structures, and we're ready to talk in serious detail about the first type of organic chemical reaction, the alkene electrophilic addition reaction.
But first, your reaction.
I thought the tape's pretty good so far as tapes go, but I wanted more car chases and some explosions possibly.
Okay.
Okay, so we're basically going to be spending the rest of this tape looking at an electrophilic addition reaction. And what does all that mean? We know that an addition reaction follows the standard formula A and B come together to form a larger product, C. And electrophilic addition reaction, well, that's almost as straightforward. In an electrophilic addition reaction, all that happens is that an electrophile adds to the reactant in the first step of the reaction.
One more point and then we're really ready to move on. In the beginning of this tape, we learned that the functional group of an alkene is a double bond between two adjacent carbons. We also learned that a functional group behaves the same way in reactions and that the functional group is where the reaction takes place.
The double bond functional group in an alkene generally reacts by electrophilic addition. It doesn't matter what alkene it is. It can be ethylene or cyclohexene or 2-methylpropene. No matter what sort of alkene you've got, its double bond functional group will always be the site of an electrophilic addition reaction. That's why it's so important for you to be able to recognize your functional groups and know how they participate in reactions.
It got kind of itchy.
Oh, itchy's not good. You should get a lotion for that.
Part 3, electrophilic addition reactions.
Section A, addition of HX to an alkene.
For our first look at addition reactions, we're going to consider the reaction between 2-methylpropene and hydrogen bromide to form 2-bromo-2-methylpropane.
2-methylpropene is the A component of this reaction. 2-methylpropene is an alkene, of course, which means it's got a double bond somewhere. And as we talked about earlier, double bonds are great sources of electron density because there are two electrons sticking out above and below the molecule in a pi bond. Because the electrons in the pi bond are sticking out from the molecule, they're really accessible, making 2-methylpropene extremely attractive to electron-deficient species.
Actually, we can make a sweeping generalization here. Because alkenes have double bonds, they are electron-rich and will almost always act like Lewis bases.
The B component of our reaction, hydrogen bromide, is the source of our electrophile. At first, it's not really obvious that HBr supplies the electrophile, but that happens like this.
Bromine is pretty electronegative. It'll pull the electrons in the hydrogen bromide bond toward itself, giving the molecule a net negative charge toward the bromine and a net positive charge toward the hydrogen.
We can show this polarization of charges along the single bond by placing a delta plus by the hydrogen, indicating that it's got a partial positive charge, and we can put a delta minus by the bromine, indicating that it's got a partial negative charge. Now let's see how these two molecules come together to form product C, 2-bromo-2-methylpropane.
The hydrogen on this end of the molecule is electron poor and is therefore an electrophile. All of a sudden, this groovy-looking 2-methylpropene floats by, with these two electrons just sitting there in a pi bond. Hydrogen doesn't have any electrons anymore because they're busy slobbering over way electronegative bromine. Hydrogen would really like to share those electrons in that pi bond, so it bails.
Hydrogen bromide easily dissociates into its ions, a bromide anion and a hydrogen cation. A hydrogen cation is really just a proton, because when hydrogen loses an electron, a proton's all that's left. The proton heads for those electrons on the pi bond between carbons 1 and 2 of 2-methylpropene.
By the way, do you see why we said that reactions occur at functional groups? They're where all the action is.
As the proton approaches 2-methylpropene, it takes both of the electrons from the double bond, forming a carbon-hydrogen bond between itself and carbon 1. Carbon 1's loving it because it still has 8 valence electrons, 4 in 2 bonds with its original hydrogens, 2 in the now single bond between itself and carbon 2, and 2 in the newly formed carbon-hydrogen bond.
Okay, so carbon 1 is sitting around with 8 electrons feeling swell, but what about carbon 2? It only has 6 valence electrons now, 2 in the carbon-carbon bond between itself and carbon 1, 2 in the carbon-carbon bond between itself and the methyl group, and 2 in the carbon-carbon bond between itself and carbon 3.
Carbon-2 is missing 2 electrons. That means it's now positively charged. Remember, positively charged ions are also called cations. This cation is now in the position to accept electrons from another atom. So it's an electrophile, or Lewis acid. We say that carbon-2 is a carbon cation, or carbocation.
This carbocation now needs 2 more electrons to fill its valence shell. Where's it going to find those? Well, let's think about this for a second. The hydrogen bromide molecule gave up a proton to carbon-1, and that's how we got the carbocation in the first place.
So when the hydrogen bromide loses a proton, we end up with a bromide anion, right? Because the hydrogen splits from the HBr molecule without its electron, and it leaves that electron with the bromine atom. So the bromine ends up with 1 more electron than it normally has, making it a negatively charged bromide anion. So we've got this positively charged carbocation over here that's looking for some electrons, and the bromide anion from the hydrogen bromide molecule just happens to be floating around. The attraction is undeniable. The nucleophilic bromide anion donates a pair of electrons to the electrophilic carbocation, forming a carbon-bromine bond.
And voila, 2-bromo-2-methylpropane. We have 2 molecules, 2-methylpropene and hydrogen bromide, which came together to form a single neutral molecule, 2-bromo-2-methylpropane, and we call the overall process an electrophilic addition reaction. It's an electrophilic addition reaction because in the first step of the reaction, an electrophile, the proton, adds to the double bond. Notice that the molecule name now ends in -ane, indicating the loss of the double bond.
Okay, now we've got a good feel for how this reaction between 2-methylpropene and hydrogen bromide takes place. But now, we've got ourselves in a bit of a quandary, a morass, a conundrum. Why did the proton choose to add to carbon-1 of the double bond, and the bromide anion to carbon-2 of the double bond? Was this all just by chance? Well, if the reaction were to occur a second time, would the product of the reaction be different because the bromide anion chose to add to carbon-1 instead? No way.
There's a pattern to addition reactions. Hydrogens, halogens, and other groups don't just bond to carbons on the double bond of the alkene at random. Vladimir Markovnikov noticed this and developed a set of rules to show that the order and placement of new additions to alkenes can usually be predicted.
What's the order and placement of new additions to alkenes?
Section B, Markovnikov's rule.
Markovnikov's rule basically says this.
The first half and the last half of my name are almost the same.
Don't listen to him. Markovnikov's rule really says this. Let's say you're trying to add a hydrogen and a halogen to an alkene. The hydrogen will prefer to bond to the carbon of the double bond, which has more hydrogens. The halogen, or any other substituent for that matter, will add to the carbon of the double bond with more substituents.
This is the fundamental premise of Markovnikov's rule, which essentially says that the rich get richer and the poor get poorer. In other words, when it comes to electrophilic addition reactions, richer carbons, ones with more substituents, get more substituents, and poor carbons, carbons with more hydrogens, just get more hydrogens.
Markovnikov's rule leads to the phenomenon of regiospecificity in alkene addition reactions. The word regiospecific literally means that the reagent adds in a very specific way. Because the addition components will always bond to an alkene in a certain order, the product of the addition reaction will always have the exact same orientation.
Under these conditions, in the electrophilic addition reaction we just looked at, there would never be an instance where the product of the reaction is 1-bromo-2-methylpropane. But there would be if we were discussing radical reactions. But we're not. We'll get to those way later, so just keep that in mind. In electrophilic addition reactions, however, the bromine will always add to carbon-2 of the double bond of 2-methylpropene, and the hydrogen will always add to carbon-1. The product of the reaction is regiospecific.
And why does this happen? What's the real story behind this observation of Markovnikov's that he called a rule? Why am I talking like this? Well, look, it all comes back to energy, my friends. Energy.
Let's take a look at the energy diagram for this reaction. This energy diagram is going to be a little different from the examples we looked at earlier because there are more steps needed to create the final product.
In our addition reaction between 2-methylpropene and hydrogen bromide, a carbocation is formed as the first step before the final 2-bromo-2-methylpropane product is formed. Remember, the carbocation is a carbon atom that is now ready to accept electrons. This carbocation is a separate entity, an intermediate that's formed on the way to forming a product. The formation of the carbocation intermediate is a separate step which has to be represented on the energy diagram for the overall reaction.
So the energy diagram for our addition reaction is going to have 2 hills and 2 transition states. The first hill represents the formation of the carbocation, and the second hill is where the bromide anion and the carbocation come together to form the final product, 2-bromo-2-methylpropane. The hill for the formation of the carbocation is higher than the hill where the carbocation and the bromide anion are put together.
Okay, let's think about this for a second. Why is the hill for the formation for a carbocation so steep? Well, the carbocation only has 6 electrons. It hasn't achieved its lifelong goal of 8 electrons, so it's sad, or, as we say in chemistry, unstable.
It takes more energy to form something that's unstable than it does to form something stable. That seems pretty logical, doesn't it? It would take a lot more energy to build a card house in high wind than it would if there wasn't any wind at all.
So, since our carbocation is unstable and higher in relative energy than the reactants, we have to go even higher uphill energy-wise to form it.
So just remember that it takes more energy to build something that's less stable than it does to build something that's more stable. Write that one down. We're going to be coming back to that one a lot.
The other thing our reaction energy diagrams tell us about reactions is how long they take to occur. The longer the hill, the more time it will take to get to the transition state. Let's check out the hill for the formation of a carbocation again.
It's a steep hill. It'd be a tough ride on a bike. So we know the reaction to form a carbocation intermediate will be pretty slow compared to the step that follows it. If we ride long enough, we'll finally get to the top of the hill, which is a special place called the transition state.
At the transition state, we get a special type of species that sort of looks like both the reactants and the products. The transition state is a funky-looking combination of the reactants and the products. At this point in our reaction between 2-methylpropene and hydrogen bromide, the transition state is where the proton is beginning to add to the double bond and the pi bond is disappearing. This transition state is fleeting. You can never isolate it. Why?
Because it's at the top of the energy diagram at what we call an energy maximum. When something is at the top of a hill or at an energy maximum, it's got one of 2 choices. It can either fall off the top of the hill toward the products, or it can fall back toward the reactants.
Because the transition state exists in this precarious place at the top of an energy diagram, it's fleeting, meaning it only has a short-lived existence, and it could never be isolated in a lab. Never!
Okay, enough about that. We need to return to the energy diagram for our reaction between hydrogen bromide and 2-methylpropene.
Like we just said, transition states occur at the highest energy point along each segment of the energy diagram at an energy maximum. After we get over the hill at the first transition state, we only have to go down to the valley, where the carbocation intermediate lives.
In the valley, the carbocation can pause for a second. It's too energetic to be isolated, but it doesn't have the fleeting existence of the transition state. This is because intermediates like carbocations are found in the valleys of energy diagrams. The valley of an energy diagram is where the relative energy of the reaction system is at its lowest, or at an energy minimum. Carbocations are at energy minima, which is just a fancy way of saying that they're minimums.
All we have to do to complete the reaction is make it over the second small hill. At this transition state, the bromide anion will attach to carbon-2 of the carbocation. When this happens, carbon-2 has the 8 electrons it needs, and it's no longer sad. Then it's all downhill from there to the final product of the reaction, which is 2-bromo-2-methylpropane. But before the bromide anion can form a bond with the carbocation, the carbocation has to be formed. Duh.
So the formation of the carbocation is the rate-determining step of this reaction. But why?
It's energetically more difficult to form a carbocation without all 8 electrons than it is for the carbocation to react further and finally get all the electrons it needs. That's why the formation of the carbocation is the rate-determining step of the reaction. The reaction has to make it over the first bigger hill before it can continue on to make it over the second smaller hill. So having said all that, the easier it is to form a carbocation, the easier it is to form the product of the reaction.
Do you see why? The formation of the carbocation is the hardest step in the reaction. It's the most grueling part of the bike ride.
But if we can make the formation of the carbocation easier by lowering the height of the hill, the bike ride won't be as steep or take as long. The carbocation will be formed easier and the reaction will be able to proceed to the products easier.
We can make an even bigger leap and say that the more stable our carbocation is, the faster the reaction will proceed to the second step and finally to the product.
Whoa! Why would the stability of an intermediate have anything to do with the rate of the overall reaction? Well, this guy named George Hammond came up with a theory called, surprise, the Hammond postulate. We need to warn you here. It's going to appear that we go in a huge big circle before we answer this question, but it's really the only way to do it. So sit tight and remember to rewind if you get lost.
Oh, and by the way, just for a little context, we've been talking about all of this to try and figure out why the proton added to carbon-1 in the reaction between 2-methylpropene and hydrogen bromide. But now, it's time to get back to Hammond's postulate.
Section C, Hammond's postulate.
Here's how the Hammond postulate breaks down. In an endothermic reaction, the transition state is at an energy level closer to the products than to the reactants. Literally. Do you see here that the products are closer in energy to the transition state than the reactants are?
And, once again, at an energy maximum, the funky-looking transition state exists, which is a little bit like the products and the reactants. Here's what Hammond's postulate says. The transition state resembles the structure of the nearest stable species. And what does that mean? Well, in an endothermic reaction, the nearest stable species is the product. Do you see that? Hammond's postulate says that because the transition state is closer in relative energy content to the product, then it just goes to figure that the transition state resembles the product.
In other words, in an endothermic reaction, because the transition state is closer to the products than the reactants in relative energy content, then the transition state resembles the products more than the reactants.
Did you hear that? George Hammond's postulate says that if the products are higher in energy than the reactants, which is what happens in an endothermic reaction, then the products and the transition state probably resemble one another. He took this all one step further and said that whatever stabilizes the products of such a reaction will also stabilize the transition state.
Did you catch that last part? We'll say it again. Did you catch that last part?
Anything that makes the product of an endothermic reaction more stable makes the transition state more stable.
Yes, that's right. You heard us correctly. If there is something in the reaction product that increases its stability, then the transition state for the reaction will also be stabilized, and that will lower the energy requirement for the reaction.
The opposite is true if the transition state is closer to the reactants than the products, which is what happens in exothermic reactions. But in exothermic reactions, the transition state doesn't look as much like the products, so how stable the product is has less influence over how stable the transition state is.
That makes sense, right? Because in an exothermic reaction, the transition state is closer to the reactants than it is to the products. The transition state doesn't look as much like the products, so how stable the product is has less influence on the energy content of the transition state.
Okay, let's go back to endothermic reactions. Let's look at the energy diagram for the endothermic step of the reaction between 2-methylpropene and hydrogen bromide again.
No.
Yes.
No.
could give you $100.
All right.
Sucker!
Before the reaction forms a carbocation intermediate, it has to pass through a transition state. This phase of the reaction is endothermic because the reactants are at a lower energy level than the carbocation intermediate, so energy must be absorbed to form the carbocation intermediate. Do you see that here on this diagram? The reactants right here are lower in energy than the products over there. So, as the proton begins to form its bond with carbon and the carbocation is formed, the energy of the system increases. Energy is absorbed to form the product, which is the carbocation intermediate. That tells us that the carbocation formation step of the reaction is an endothermic process.
If we keep going with all of this, the transition state of the reaction is closer to the carbocation intermediate than it is to the reactants. Do you see that here?
Hammond's postulate tells us that if the transition state is closer in energy to the products than it is to the reactants, then the transition state probably has structural and electronic characteristics that resemble the products more than the reactants. So, if we apply Hammond's postulate to this endothermic phase of our reaction, the transition state will look a lot like the carbocation intermediate that's formed in the first step of the reaction between HBr and 2-methylpropene. So, anything that makes the carbocation more stable will make the transition state more stable.
Here's the point that we've been taking so long to build up to. In the phase of the reaction between 2-methylpropene and HBr, where the carbocation is formed, the alkene and proton actually have a choice.
The proton from HBr could add at carbon 1 and form a carbocation at carbon 2, or the proton could add at carbon 2, forming a carbocation at carbon 1.
Okay, now we know there are two choices as to which carbocation is going to form, and molecules, just like everything else, are looking for the path of least resistance. Once again, it all comes down to energy, my friends, energy! You see, we need to figure out which of these two possibilities increases the potential energy of the system the least, because that's what the reaction's going to do. You see, it's going to look for the path of least resistance.
It turns out that a carbocation with more carbons attached to it is more stable than a carbocation with fewer carbons attached to it. Why? No, not because it has a wonderful family life, but because the carbons attached to the electron deficient center can feed electrons to it, helping to stabilize it somewhat. In practice, this means that a carbocation with more carbons around it is going to be more stable than a carbocation with fewer carbons around it.
Remember, when we talk about the stability of something, we're really just talking about the potential energy of that something. Like we said earlier, it takes less energy to build something more stable than it does to build something less stable. Let's think about this for a second and figure out how it affects the outcome of where the proton adds to our alkene.
If the hydrogen adds to carbon 2 of the double bond, then carbon 1 ends up with the positive charge. Carbon 1 ends up being the carbocation. And like we just said, a carbocation is more stable when there are carbons around feeding it electrons. But when the hydrogen adds to carbon 2, so that the positive charge is at carbon 1, there's only one other carbon around to help stabilize the carbocation. So the carbocation at carbon 1 ain't all that stable.
The carbocation at carbon 1 is what we call a primary carbocation. It's only attached to one other carbon, so it's primary. If it were attached to two other carbons, it'd be called a secondary carbocation. And if it were attached to three other carbons, it'd be a tertiary carbocation.
Like we just said, if the proton adds at carbon 2 so that the positive charge ends up on carbon 1, then the carbocation is a primary carbocation, meaning it's only got one other carbon feeding it electrons. But if the hydrogen chooses to add to carbon 1 instead, so that the positive charge ends up on carbon 2, then there are three carbons around to help stabilize the carbocation. There are three whole carbons around to help the carbocation in its time of need. The carbocation that forms is a tertiary carbocation, which means it's got three carbons around it feeding it electrons.
Carbon-2 is more highly substituted than carbon-1, so carbon-2 can deal more effectively when it gets stuck with the positive charge than carbon-1 can. Carbon-2, the more highly substituted carbon, is more stable when it gets dealt a positive charge than less highly substituted carbon-1.
Now, in our reaction, a carbocation with more substituents is energetically more stable than a carbocation with fewer substituents. So, going back to Hammond's postulate, if our transition state looks very similar to the carbocation intermediate, and if a carbocation is more stable with more substituents, we can make a pretty good guess that the transition state will also be energetically more stable with more substituents.
We're going somewhere with this. Just hold on. Here's the center of this whole discussion. If our product, the carbocation intermediate, is more stable because it has a carbocation with the most substituents possible, then the transition state forming it is more energetically stable, and the reaction proceeds faster.
Whoa, you're saying. Where'd we get that from? Well, the transition state is the highest energy point as we go along the reaction, right? So, if a transition state is energetically more stable because it's got a carbocation with the most alkyl substituents possible, the transition state for that step will be lower in energy. The hill will be smaller. It'll be easier for the reaction to climb over the transition state hill on its bicycle.
All right, do you get it? Do you see that the more highly substituted the carbocation, the lower the energy for the transition state, the lower the hill the reaction has to climb to form products, and the faster that product forms. And that's why hydrogen adds to carbon-1 of the alkene rather than to carbon-2. It's just easier and doesn't take as much energy.
Hammond's postulate says that because the transition state is closer to the products than to the reactants, the structure of the transition state will look a lot more like the product, which in this case is the carbocation intermediate. And anything which makes the carbocation intermediate more stable will make the transition state lower in energy content. The hill for the transition state won't be as high, literally, and the reaction will go faster.
So let's take all of this newfound knowledge and apply it to the reaction between 2-methylpropene and hydrogen bromide. Let's look at our carbocation intermediate again. If you remember, we got into this whole discussion because we were trying to figure out which carbon of 2-methylpropene the proton from hydrogen bromide should add to.
Over here, we have a primary carbon. And here, we have a tertiary carbon. And over here, we have a big wheel. Once again, it all goes back to energy, my friends, energy. You don't want to expend all sorts of energy if you don't have to, right? You may think it comes from sheer laziness on your part, but we can basically guarantee that it's ingrained in you because your molecules are doing the same thing.
Like we said, in the first part of the reaction, when the proton adds to the alkene to form the carbocation, the proton has a choice. It can add to carbon-1 or it can add to carbon-2.
Let's say the proton hits up carbon-2 first. That would mean that the positive charge would end up on carbon-1. That would be a much less stable carbocation because carbon-1 only has one other carbon feeding electrons to it, helping to stabilize it. The transition state skyrockets in energy, and the transition state thinks, "No way! I'm not expending a drop more energy than I need to. Go away. Shoo!"
The transition state was so stressed out that the proton wanted to add to carbon-2 that its resting energy level rose, causing the transition state for the formation of the carbocation intermediate to go up really high. The energy level goes up so high it's an almost impossible bike ride, so the carbocation isn't formed at carbon-1 very often.
So then the proton hits up carbon-1. If the proton adds to carbon-1, then the positive charge ends up on carbon-2. And carbon-2, well, let's just say that carbon-2 is a horse of a totally different color. In fact, it's tertiary colored. Okay, it's actually puce, but that's not important right now. What is important is that carbon-2 is a tertiary carbocation. It's got 3 other carbons bonded to it.
The proton approaches carbon-1. Carbon-2 thinks,
"Oh no! If that proton adds at carbon-1, then the positive charge is going to end up on me. Oh no, oh no, wait a second. I'm a tertiary carbon. I can deal with a positive charge because I've got 3 other carbons around to feed me electrons. I can handle this.
Come on in, proton. Add to carbon 1. I can take it.
So the proton adds at carbon 1, the positive charge ends up on carbon 2, and it ain't no thing. Carbon 2's got no big problem with the positive charge because it's a tertiary carbon. The transition state doesn't get as worked up, so it's not as high in energy. The hill is lower and the bike makes it up the hill more easily. The reaction proceeds to formation of the carbocation faster because the lower transition state means a smaller hill and an easier bike ride.
So, in our reaction between HBr and 2-methylpropene, the proton adds to carbon 1 faster, and carbon 2 now has a positive charge and is the carbocation. The carbocation only has 6 electrons in its outer shell, and it needs 8 to complete its octet. And the bromide anion has electrons to share. It comes to the carbocation's rescue. The bromide shares its electrons with the electron-deficient carbocation at carbon 2, and we have 2-bromo-2-methylpropane as the product. The transition state for the addition of bromide was lower in energy than the first step, so the reaction proceeded from carbocation to final 2-bromo-2-methylpropane pretty easily.
We're in a state of confusion, ladies and gentlemen. Thank you very much for being here. I really appreciate it. You've been wonderful.
Okay, major conclusion here. If the reaction can proceed to the transition state more quickly because the product it relates to is more stable, then the reaction can go to completion faster.
Okay, there's a sort of shorthand way for representing the overall goings-on of a reaction. We just looked at an electrophilic addition reaction between hydrogen bromide and 2-methylpropene, which came together to produce 2-bromo-2-methylpropane. Now, how do organic chemists represent this general type of reaction using their shorthand methods?
Well, the hydrogen bromide is represented by HX. H, of course, is the hydrogen, and X is the halogen bromine. The halogens are a special group of elements found in column 7A of the periodic table, and they include fluorine, chlorine, bromine, and iodine. So, we've got HX for the HBr component of the reaction.
Now we need to represent our alkene to methylpropene in some sort of shorthand method as well. We represent the alkene like this. We just show 2 carbons linked with a double bond, and we show that the carbons are also bonded to other things with single bonds by drawing in these open-ended lines.
Drawing the alkene this way, we're saying to everybody, look, there's a lot more going on in this molecule, and we're aware that there's a lot more going on in this molecule. But because those other things really aren't involved in what's going on in the reaction, we aren't concerned with them right now. We're only looking at the carbons of the double bond because they make up the functional group, and they're where all the action is. In other words, we know that all that other stuff is there, but we're ignoring it. And we can do that, as long as we draw on these 4 lines.
So, we've got HX and an alkene, and all of a sudden we have a really general expression for addition of HX to an alkene. Our product, 2-bromo-2-methylpropane, is going to look like this. H adds to the less substituted carbon of the double bond, and X adds to the more substituted carbon of the double bond.
I know. We can't tell which carbon of the double bond is more substituted, but neither can anyone else. They just have to take our word for it that the H and the X have added to the double bond according to Markovnikov's rule, with H adding to the less substituted carbon of the double bond and X adding to the more substituted carbon. But in order for them to take our word for it, we have to say that H and X add to the double bond following Markovnikov's rule. So we just say that right here, Markovnikov's rule is observed.
So, do you see what we've got here?
We've got an HX adding to an alkene, yielding a product with an H and an X on the carbons of the double bond. And by saying that the reaction follows Markovnikov's rule, we tell anyone looking at our reaction that the hydrogen, H, adds to the less substituted carbon of the double bond, and that the halogen, X, adds to the more substituted carbon of the double bond.
And if you thought that was cool, just wait. This is where things really start to get crazy in organic chemistry. Look at the generalized formula that we just came up with for this reaction again. HX doesn't just have to be hydrogen bromide. X can be any halogen. Yep, any halogen. You got it. So it could be chlorine or bromine or iodine, and our alkene can be any alkene. It doesn't just have to be 2-methylpropene. It could be methylcyclopentene, 1-butene, any alkene.
So, all of a sudden we have a template of sorts for the addition of HX to an alkene. Anytime you add HX to an alkene, you get an alkane with H added to the less substituted carbon, and X, which can be chlorine, bromine, or iodine, added to the more substituted carbon.
And that's the point you really need to get out of this whole discussion. On a test, if you're asked to predict the outcome of an addition reaction in which HX adds to the alkene, you need to be able to tell the professor that H adds to the less substituted carbon of the double bond, and X adds to the more substituted carbon, and then you have to name the product. Of course, you need to remember why you have this template in the first place, which really all goes back to Markovnikov's rule, which really all goes back to Hammond's postulate, which really all just goes back to energy. It all comes back to energy in the end, doesn't it?
Now let's try to apply this marvelous template of ours. Say your professor asked you to tell her the product of a reaction between hydrogen bromide and methylcyclopentene. You panic, you sweat, your eyes dart around the room, and then you think, oh wait, I can do this. This is just the addition of HX to an alkene. No problemo. Let's draw it out.
On the left side of our arrow, we've got methylcyclopentene. On the arrow, we've got HBr, because that's the halo acid we're using. From everything we just learned, we know that the proton is going to attack the alkene first. It's going to pick the less substituted carbon of the double bond, so as to leave the positive charge on the more substituted carbon, which is better equipped to deal with being the carbocation.
So the proton adds at carbon 2 of the double bond because it's got fewer substituents, and that makes carbon 1 the carbocation. Then the bromide anion moves in and adds to carbon 1. Do you see how this follows our template? H adds to the less substituted carbon, and the halogen X, which in this case is bromine, adds to the more substituted carbon. The product is 1-bromo-1-methylcyclopentane. Markovnikov's rule was observed. The more stable carbocation was formed. The transition state for its formation was reached sooner, and all was groovy.
Yeesh, we beat the addition of HX to an alkene to death.
And that's it. We've come to the end of our long journey. In the deep-fried world of organic chemistry, part 2, we've covered a lot of ground. We've gone over alkenes, reaction energy diagrams, addition of HX to an alkene, Markovnikov's rule, Hammond's postulate, and a whole lot more.
In the deep-fried world of organic chemistry, part 3, we're going to cover a boatload of electrophilic addition reactions. All of the fun stuff we just learned in this tape is going to come back to haunt you again in tape 3. So make sure you know all this stuff backwards and forwards.
Rewind, fast forward, rewind, fast forward.
Once you know this tape inside and out, you'll be ready to take on all sorts of electrophilic addition reactions with freaky names like hydrogenation, hydroboration oxidation, oxymercuration, and a whole bunch of other Asian things in the deep-fried world of organic chemistry, part 3.
In part 3, we'll discuss 10 more alkene electrophilic addition reactions, and we'll introduce you to the alkynes. We'll also talk about alkyne electrophilic addition reactions, including the halogenation of alkynes, alkyne mercuric ion-catalyzed hydration reactions, and more.
Thanks for watching. If you had any problems or you just want to tell us how keen we are, give us a call here at Cerebellum at 1-800-VCR-REVIEW. We'd love to hear from you.
And make sure to pick up our other video course reviews on such subjects as accounting, astronomy, physics, psychology, Spanish. We got them all. They're all from
The Standard Deviants. Bye-bye.
Bye-bye.
Ow. Ow.
If reactant AB cleaves
Covalent bonds can be broken in two ways, heterolytically or homolytically. You can even say things like, I'm sorry, that's the wrong card.
Luck be a lady tonight.
Margarine contains partially hydrogenated vegetable oil.
From the number 1, carbon. Sorry.
Oh,
is closer to the carbocation in
Height of the hill on the diagram.
You guys!
The reactants are on the left side of the hill.
Does any of this talk of electrophile?
But that won't always be the case.
You don't care, Mama.
Don't lie.
Between two.
But the double bond portion of alkenes.
2-methylpropene and hydrogen bromine.